Afternoon, I think, is everyone on the call because it's morning here for us in the U.S., but it looks like we might have. I guess Eric, you're in Boston, so still morning for you, so that's good.
Yep.
All right, thanks for joining. So everybody, thanks for coming. This is ScaleChem Basics web training. I'm so glad to see, particularly the folks from Asala. I know we've had some trouble getting you connected. And so very glad that you could make it to join us today and hopefully Wednesday as well. So what we're going to do, I don't know if I want to go all around the group just because it's a bit large for full introduction. So I think we'll maybe skip on that this time. But basically, so we'll skip this, the first introduction. I do that if it's a small enough class, but I think because of the size, maybe we'll skip that today, but we'll give a little bit of background on OLI, and then we'll talk a little bit about our simulation capability, the things that we can do, how we can help model, particularly scale in this case, and then we'll turn it over to Diana Miller, who is the instructor for today. My name is Mike Kochever. I lead the sales team here at OLI, so if you have questions about for those of you who have licenses and have access to the software, if you have questions about that, how to get more training, how to learn more about the software, I can definitely help with that. So, obviously, anytime you have questions, we want you to reach out to us here at OLI so that we can make sure that you're getting the most out of the software that you have. So, a lot of you may know this already, but let's talk just a little bit about OLI. So OLI has been in business almost 49 years now studying electrolyte chemistry. I'm just going to grab a quick pointer here. So in that time, we've developed an extensive properties database, always looking to model electrolyte behavior the most accurately and the most broadly that we can. So we want to cover a lot of chemistry, and we want to do it very, very well. So OLI has always had a mission to further that electrolyte science. We do that mainly through software. So some of you may have worked with us as on a consulting basis, either with Diana or AJ or someone else on that team. But more typically, we like to have the software in your hands. You guys are the experts in your industries with your projects, and we want to make sure that you can understand how to use the software to the best of its ability, because you really are the ones who understand your process, your applications the best. And so we can provide that tool for you to understand really what the systems are that you're working with. So there are a few different ways to work with OLI software. We're going to focus today on the chemistry side. Well, today and Wednesday in the course, we're going to focus on the chemistry side, specifically in OLI Studio and ScaleChem. So this is an upstream oil and gas tool, is how it was designed anyway. It can be used elsewhere if you understand the internals of it, but essentially designed to predict mineral scale in an upstream production environment. So that's where we'll focus our time. OLI Studio also is paired in the foundation product of Studio as Stream Analyzer. So this is essentially, you think of it like a virtual laboratory. So if you were doing something in a lab, working in a beaker, you can run a lot of those same tests on a sample, what we call a stream, in the Stream Analyzer. So these two often get paired together. ScaleChem being a focus on the production and the scale prediction, and Stream Analyzer allowing you to go a little bit more in depth in understanding the behavior of the electrolytes that you're working with, the water chemistry. The third component of OLI Studio is the corrosion analyzer. So I don't know if anyone on the call has had a chance to work with that, but that allows us to take that same stream, that same brine, put it in contact with the metal surface, and now we can start to look at predicting things like corrosion rates and doing material selection. So we'll talk a little bit about that just as an introduction, although we don't have any examples using corrosion analyzer in this course. There are other courses that we have if you want to learn more, or we can just talk through it offline. A third way that we work is in flow sheeting. So whereas the OLI Studio focuses on an individual point or an individual stream, the flow sheet tools allow you to look at a full process. And ScaleChem actually has some of this on a limited basis as well. Diana will show you that and how you can create sort of a simplified flow sheet to study scale. But when we talk about full rigorous flow sheets, two ways that we work. We have our own tool, OLI Flowsheet ESP. So when electrolytes are the focus of your modeling, say at a water treatment plant, this is a great tool to start to look at the full process and how changes in feed conditions maybe, or if you want to adjust pH, how does that affect the overall process? And you can study everything throughout rather than just looking at one point in time. We can also work inside of what we call our alliance partners. So these are connections that we've made to other software, whether it be with Aspen, we have Aspen Plus and Aspen HYSYS. Aviva has Pro 2, Honeywell's Unisim. There are others that aren't on this list. But essentially what you do there is if you already have a model in one of these other tools, we can bring in OLI technology or OLI's calculations as a property method. And so you can use our ability to handle the electrolyte side of things in those tools if you already have them. Obviously, a big key here is if you've already got models built and you have expertise in that tool, we don't want you to have to necessarily learn new software to be able to run that. And finally, we can do some custom applications. So two different directions here in that we can connect OLI's engine and the solver into a third-party software. So if you have your own proprietary software that's doing calculations and you want to get electrolyte data from OLI, we can make those connections via an API. And we're also looking to automate some of these systems. So one idea is, if you have a historian on a plant, maybe we can pull data from that and actually have scale predictions or corrosion predictions live in almost real time. It's not continuous, but you can pull it regularly to sort of understand the behavior or the predictions that you're facing. So if anybody has interest in something like that, obviously not covered in the course, but let us know and we can talk it through. So today we're going to focus in upstream oil and gas, again with ScaleChem, namely mineral scale prediction. Prediction, that's the baseline technology here. We'll do some, and it runs really, from all the way from planning stages through drilling and completion. We can look at some flow assurance issues as your production proceeds. Water treatment. There's another one over here that I would have added for injection. So if you're now doing enhanced recovery and injecting other additional streams, we can look at how those behave in the system as well. So we'll talk about this was what I was mentioning before, the well profiles, where you kind of see the behavior and where scale may be predicted up through the full production line. Injection waters, gas lift. Sometimes this is interesting for folks, either methanol or glycol regen processes. We can look at those. And then I mentioned down here these last couple, we won't do it in the course, but we do have ability to start looking at materials of construction as you go through. So many of you will know that there are 3 different frameworks inside of the software, and the one that we're going to focus on today is the newest of the 3, actually, from OLI, MSE SRK. So this combines our own MSE, or mixed solvent electrolyte framework, which is essentially a method by which we calculate the properties of a stream. And then we built this additional SRK term in because we were getting some discontinuities in the calculations using only MSE at the extreme conditions for upstream. So very high temperatures, very high pressures. And so we evolved the MSE SRK to really get the most accuracy for the particular systems that you guys will be interested in the upstream environment. So that's where we'll focus today. And really, if you're doing scaling calculations, we would probably recommend that you're in this framework anyway. I think I'll skip the rest of that. It's another bit about here about MSE SRK. Again, it's the focus of it is those extreme conditions and needing special calculation methods to handle those types of approaches so that we get accurate results. It applies to all of our chemistry, so what we call the standard scales, and then across the full range as well. So we can use all of that, and it as well, it goes into OLI flow sheet. So if you start using that tool, you can carry it right in from ScaleChem. So just a bit of background on the software. When we use the OLI Studio, or really any of our tools, we're looking at equilibrium-based calculations and 4-phase distribution. So we have a solid, a liquid, a vapor, and a second liquid phase, which is typically inorganic. So we're going to look at how the various species distribute amongst those 4 and go to equilibrium. During that, we'll calculate a list of physical and chemical properties. We can do things like kinetics. We don't have kinetic data in the software, but there's a way for you to enter that if you do. So if that changes the behavior of your system using the kinetics, we have a way for you to enter that. Redox chemistry can also be important. We handle mass transfer, surface complexation reactions, and then some other, advanced properties, oxidation reduction potential, activity of water, transport properties, and then osmotic pressure can be important as we move into the water treatment end of your systems. So when we look at ScaleChem specifically, then, again, the 4-phase calculations and the physical and chemical properties, we're going to look at what we call our standard scales: carbonates, sulfates, halides, and then it expand across a wider list of chemistry as well. So when we talk about the sort of upstream high pressure, high temperature environments, we focus, or we've well studied calcites, barytes, calcium sulfate, as you see, and then lead and zinc sulfate, or sulfide as well, excuse me. So large coverage for us. We're going to look at different ways to do scaling scenarios. So how do we study scale? How do we understand how it's forming? We're going to see what the scaling tendencies are, where they're expected to occur, and then how we can actually predict as well how much of that we can see. We'll talk show you examples of mixing waters calculations. So are these waters incompatible, and they might be causing problems if you're re-injecting or something like that. Saturation for reservoir conditions. So this is taking a sample at the surface, and we can actually back calculate what that would look like at the bottom hole. So we can start to understand the gas, oil, water partitioning as you move backwards. Facilities, Diana will show you. That's an additional feature of ScaleChem. And then we can also start to understand scale prediction in pipelines. We won't talk about this last one here in the course with Pipesim. This is a Schlumberger product that we've partnered with, where you can actually start to look at how that works inside of pipelines. I mentioned before the split between the flow sheeting models. So just another quick example here where we've got flow sheet on the right with where electrolytes are primary, and then our alliance engines maybe where It's more of a hydrocarbon type process, but you have a specific area that needs electrolyte modeling. You could bring OLI in there as an example. And here's just a quick one on the corrosion piece. So we can generate pore bay diagrams if that's something that you need to take a look at. General corrosion rate, so mils per year type of corrosion rates of equipment or piping. And then we can also go a different way and look at localized or pitting corrosion. So this is a different approach that we take to the science there. I think that is probably all that I want to say by way of introduction. So I think without taking any more time, if anybody has any initial questions, please, it looks like everyone's on mute, so just unmute yourself if you have any questions. You can ask us directly. And otherwise, I am going to stop talking and turn it over to Diana.
Thank you, Mike. Okay. I will just share my screen and see how it goes. And just let me know if you can see it and if you hear me okay.
Hearing you fine, yep. And I do see this share, yep.
Perfect.
Set me up.
Great. Okay. So just one thing, Mike, I think that before with WebEx, I would be able to see the questions. I don't know how I will see questions here. Maybe let me put this to the right, just to to see the chat.
Yeah, you can bring back up the window, and I'll share the chat as well. So yeah, that's a good point, guys. If anyone has a question and you're don't feel like speaking, you can use the chat function and just message Diana or myself or everyone, and we'll make sure to get questions as we go. So definitely stop us as we're going with questions that you have, so that we can make sure everyone's clear.
Yeah, I just want to make sure that I have them in front of me. I don't want to miss them. Okay, perfect. Thank you, Mike, for all of the introduction, and thank you everyone for being here today. I don't know, good morning, mostly good afternoon for everyone. And today we will be learning the basics of ScaleChem. So that's why we call this course ScaleChem Modeling Basics, because we will learn basically how to set up a basic calculation, where the things are, how to be comfortable with the software, and then start creating your own models or your own simulations. So as a quick note, I just want to mention that I will be using the latest version of OLI software. That will be OLI Studio v10. So if you are using an older version, you may obtain slightly different results, but still within the same, more or less the same values, but maybe slightly different results. And we will be also recording this session so that you have access to it whenever you want to remember how to do certain types of calculations. So you'll have it as a future resource. These are the main course objectives, but I think that, as I mentioned before, the most important objective for me is that at the end of this course, you will be able to simulate any simulation that or any problem or issue that you have in the field, and you will be able to reconstruct it in the software, and also how to interpret the results of the simulation in the software. Our goal is to get everyone comfortable entering data and learning where to find the critical information. This is the course agenda. So for day one, we'll be covering basically the chapters of the training manual. Today is mostly mechanics, and then we will start with some case studies. And I just want to mention that if you have any cases that you want to create, or you have some questions, please write them down and let me know today so that I can think about them, and I can start with those as some examples for the next class. So again, I'll go through the mechanics, but if you have any questions or any case that you would like that I cover, just make sure to let me know, and I will start with that next class. So the training will be divided into 2 days, and each session will be around 3 hours. No, it will be 3 hours, but each session will be 53 to 55 minutes, and then we will take a short break of 5 to 7 minutes. And also, I just want to mention, ideally, it will be nice to have 2 screens so that you have your software in one screen and then you have the presentation in your other screen. If that's not the case, you can always split your screen to see the presentation and work with the software at the same time. So if you happen to have one screen, what you can do is use your keyboard. And if you use the key, or this is the Windows key, and the left or the right key in your keyboard, then you can split your screens. This will make it easier for you to follow the training. Regarding the materials for this class, we will be following the OLI Studio ScaleChem basics. This is the manual. I think you may have access to it as of today. And also, I will be going through this essence of the manual, and at the end of the day, I will provide the files that we create during this class. And I just want to make sure that everybody is installed, that everybody has the software installed. Ideally, it will be nice to have the versions above 9.6.3 because we will be working with the MSc SRK framework for this class. So let me know if you have it all installed, and if not, we can just help you to get up and running so that you can use the software as we go in this training. So during this course, please let me know if you have any technical issues, as I mentioned before, specifically the software. If you're leaving the course, also let me know so that if I'm calling your name, I don't get freaked out about if maybe you lost the connection or something. I will be, as I mentioned also before, I will be recording this session so that you can have it for your future reference. So please mute or turn off your devices so that we don't have any disruptions during the class. And please feel free to participate anytime that you have any question. You can either raise your hand. In Teams, I noticed that if you move your mouse on the screen, it will appear, a bar like this will appear on your screen. So then you can either unmute yourself and ask a question, or you can raise your hand, or you will have access to the chat window, to the chat version here. When you see that it's like a little bubble. So you have those 3 options to communicate with me. And Dira and Mike, I see that Greg, he says that he doesn't have the software installed, so maybe we need to send a trial serial number or something so that he can get up and running.
Yeah, Greg, from the invite, the email invite, you will find there the link for the installation. I'll resend it right now for you, so that it will be easier. No worries.
And also Dennis.
Yeah.
Shed. Mm-hmm. Perfect. Thank you. Thank you for your help, Dira. Mm-hmm. So at the end of this course, you will receive a certificate of completion, and you will also receive a survey where you can rate this course. Okay, so let's get started. So ScaleChem. ScaleChem is considered, or is like when Mac was talking about ScaleChem, you can see this as an add-on of OLI Studio. OLI Studio is basically an umbrella that contains 3 different tools. It will contain the Stream Analyzer, it will contain ScaleChem, and Corrosion Analyzer. In today's session, we will focus only on the ScaleChem, and this ScaleChem can be seen as a thermodynamic tool that will help you to predict mineral scaling, scale mass, and also at which locations during oil and gas production you will have that scale information. It will help you to compute the properties of gas, oil, brine, and solid phases. It will help us to construct a representative fluid composition when we have experimental data, and that experimental data is limited. And it will help us to quantify risk of unexpected production problems, and also will help us to design, do some production design and treatment decisions. So the first thing that we're going to do is to learn about the OLI Studio desktop user interface, because in this user interface is where we will be able to create, analyze, and interpret the results of our application chemistry. So I will start talking about and describing each one of these windows. And then what we're going to do now is let's go and start and open the software. So you will see in your desktop, you will see this icon that says OLI Studio 10. Just double click on it and open the software. Oh, it opened in another window. Okay. So please let me know when you have the software. Oops. It's different to work with Teams. I'm used so much to WebEx. Where did it go? Okay. So the first thing that you will see when you open the software is this interface here. And I will start describing the navigator panel. So for the navigator panel, we have that is shown here in this upper left corner. The navigator panel is the field where you will see which files are open at a given time. Okay, the name of the file that is open will be given in this header right here. Right now, you'll see that by default, this document has been called document 1. And we can save this document 1, we can save the name, we can change the name and save it as ScaleChem Training Day 1. So we'll go to File, Save As, and please select the location where you want to save this file. I will save it under my ScaleChem trainings, and I will name it ScaleChem Training Day 1. You'll see that now the name of my file has changed. You can also, let's say you have previously created a case, so you can also open a previous case. Oops, file, and maybe I want to open this case here. And maybe I want to create a new case as well. So I will just use this new, this blank page icon here, and I will create a new one. So why am I showing this? The reason is because in the navigator panel, you can have different files that you need available. And this will make them, it makes it easy to access them at one given time. Like if you want to, let's say, check the results from this file and then you want to go back, so you have them available to you. Now let me just quickly, with this example that you see to the left, I want to talk about also some icons that you see here in this navigator panel. Okay, so these icons that you see here, you'll see different icons that we will go through them that come from this actions panel down here. You'll see different icons, and you also see a different hierarchy here. So you'll see that, for example, I have named this one Olympus 1 brine, and below it you see a substream. So why am I calling it a hierarchy? Because what happens is that when we create any of these objects in this navigator panel, we need to specify that every time that we create these objects, if we specify, let's say, the temperature and pressure and the units in this level up here, then everything will be carried down to the sub-level. So for any Word file, I will stress this point that anytime that we are creating a new file or a new object, let's make sure that we have our desired units and our desired framework, because when you start adding and adding more calculations below it, then it will have those units, and then if you want to change units, it will become a little bit overwhelming. So if you know the initial units that you want to work with, then it will reduce the amount of time when you're building your simulation. And I'll go through it during this training. Additionally, I want to show that, let's say, for example, you have created a specific object in this navigator panel, and then you want to put it into a new document. You want to copy and paste it. So let's say I want to use this Olympus One brine example of this object, and I want to copy it or take it to a new document, document 2. So what I'm going to do, I have two options. I can either right-click on it and copy, and then I go to document 2 and right-click on it and then paste. So now I have the same file that I have previously created in this new document.
Hi, Dinah.
Yes.
It's Clay speaking here. When is it your document 2 appearing? It's basically as soon as you already describe your stream. Is that when you now have document 2 appearing?
Say that again. Like when you
when do you have document 2 appearing? Like a set of I would say project appearing, because for the moment I only have the stream 1, which was changing to ScaleChem training.
What I did is that I just added, you see here, there is my new open and save. So I have this new document here, and I just created.
Okay, so those are basically your documents that are stored into your folder, basically. Some of your projects that you worked on.
Yes,
okay.
So, right. I'm just using it for demonstration, and we will create them.
Okay, I understand that. So when you were talking about the exporting or copying some of the stream into a new project, is that the case when, for example, you want to do some sensitivity analysis? Let's say from the result or the output that I will have from the ScaleChem training day 1 project, for example, and you want to see if I keep the same level of information, and then I bring it to another project, and then from there I'll probably change some of the properties. Is that the case here?
No, in here everything is broad, everything is copied, units, the thermodynamic framework, and even the results. You'll see that you see this check marking here. It brought it all calculated, everything exactly the same as you had it in your previous case.
Okay.
So everything is literally copied and pasted, and nothing changes when it goes from one project to another one.
Yes, I understand. So when it goes from one project to another one, it's fine. So, but you can use then that option to, let's say, amend some of the properties from your project 1 into project 2 to just evaluate the impact of changing some of the properties on your output result. Is that okay?
Yeah, you can do that as well.
Okay. That's what I wanted.
Definitely. And we will see some of those changes later in the examples as well. We will make some changes to the brine and see what happens. And maybe what you can do is copy and paste to see the differences as well. But yeah, the answer to your question is yes, you have that option. Okay.
Thank you, Diana.
No problem. So that is one of I was talking about the copy and paste option. And you can always, you have that option. The other option is if you don't want to copy and paste, you can always just drag and go to the document of interest and just put it in there. Oops, it says that it's not valid. Let's see, Olympus brine, document 2, and I'll bring it here. So I will bring my brine to that document here. So just dragging will also do that. So that's basically the essence of this navigator panel. it will just allow you to access different files at the same time, copy and paste, see the hierarchy of your case, etc. So that's a navigator panel. Now there is another panel that I also want to talk about, and is the actions panel. So with the actions panel, let me go back here. It will be this panel that you see here. I'm going to make it a little bit bigger, where you see all of these icons, okay? In this action panel, basically you will see the objects that are installed in the software, and these objects will depend on the add-on that you have. So in this case, if you only have ScaleChem, for example, you will see only these objects that I am showing here. If you have all of the 3 packages, then you'll see all of these objects here, where you will see a stream analysis, a mixer, water analysis, etc. But if it were only ScaleChem, you'll see only these 8 icons in here. There is a different way of representing these icons here that I personally prefer, and that is the view list. So I'm going to change it, and if you want to change it, we can do it in the following manner. So if you right-click on it, on any white space area of this actions panel, then you can select the option list. And I personally prefer it this way because it takes less space and you can see all of the objects at one time. Okay, so that's the actions panel. We also have the plot template manager that I will go through also during the training. And the next one that I want to talk about is the toolbar. The toolbar section, where we can have quick access to different functions. So the most used ones that we'll be using a lot today, and that probably during our simulations that we will use a lot, is the file option, the chemistry toolbar, and also the tools. So again, let me bring the software. So that toolbar is located at here. And regarding the chemistry toolbar, I want to talk about what each button in here means. The L1 button stands for liquid 1, or the aqueous phase. We have a VA that stands for vapor phase, SO for solid phase, L2 for liquid 2 phase, or organic or hydrocarbon phase. And if we are doing some redox, or we are doing some, let's say, corrosion rate calculations or Corvey diagrams, so then we'll be using this redox reaction button. And the next 3 ones in here, these buttons will be the thermodynamic frameworks that Mike mentioned before. So those will be the MSc, SRK, and AQ. We will be using the MSc SRK for this training. So whenever you turn on any of these options, they will be highlighted in blue, on this light blue. When they are off, so they are grayed out. Then you'll see also this toolbar to the right. This is where you have different options. The first one is these binoculars here. This is the component search. So if you open it, basically with this component search tool, you can search for components that maybe you don't remember the formula, or you're not sure how to enter it into the software. This tool will help you. You just type, let's say, benzene, and it will give you all the information of benzene, molecular weight, gas number, formula, and even the structure. Okay, so that's very useful to know that exists. The other option that you'll see here is this names manager. You'll see that it says, this is very tiny, but if you go very close, and you'll see that it says NaCl salt. What that means is that this is the way that you have 3 options to present the names of your components that you enter. The first one is display name. So you'll see once I use the name, once I select the display name, you'll see that now all of these cations and anions have changed to name. So you will say sodium ion, potassium ion, calcium ion. Then the other option is formula, is the default option. So this will be more like what a chemist will use, or when you see a water analysis, this is how it will be represented. And then is the OLI name. And this is the naming that we internally use in OLI for our coding. So this one is not very useful in general, but the two that are mostly used is the formula or the display name, whichever you feel more comfortable with. So I will leave the formula name on and click OK. Then finally, I want to talk about this units manager. This units manager allows you to select or change the preferred units of your calculations. If you click on it, it will open up a new window where it says that the current object that I am selecting has metric units, and those metric units for all the components that you have is showing them as concentration units. So if you want to know more about the units, then you go to the Customize button, and it will open up a more detailed units manager. So in here, you'll see that your stream amount is defined in liters, your inflows is defined in concentration in milligrams per liter, that any output variable will be in concentration for the aqueous composition, it will be in milligrams per liter. If it's the vapor composition, mass percent, etc. You can always change all of these units down here in the basis option. So if you, for example, don't want milligrams per liter as the concentration, you can simply just change it to grams per liter or any of these options that you see here. If you don't want liters as volume, you can select any other unit that you prefer. But at the moment, I'm not going to make any changes, and this is just for demonstration purposes. So I'm going to cancel this. And that is the toolbar. We will be using it during the training as well. Okay. Finally, regarding the user interface, I want to talk about the workspace. Why is it not showing this? Okay, the workspace. The workspace is this one that you see here in the middle of the screen. This is where we will spend most of our time, where we will enter our chemistry and analyze our results. And depending upon the selected object that you have in the navigator panel, you will see a different configuration for this workspace. So for this specific brine analysis, for example, we have a description tab. We have that in this description tab in here, we can change the name of the object, and we can add descriptions for that selected calculation so that we don't forget what specifically we were doing with that calculation. Then we have the design tab or the definition tab, where in here we will enter our composition of the stream, or for this example, for this water analysis. Then you'll have the report tab, and in here you will see a series of tables with all the inputs and all the results of the simulation. And we will learn how to interpret each one of these tables during the training. But as we start also creating some other objects, we will learn how to identify each one of these tabs in our workspace. Okay. One last comment before we start working in the software. So the three thermodynamic frameworks. The MSc SLK framework is the one that we are going to use. This was developed for upstream and oil and gas applications. And whenever you have pressures above 80 atmospheres, this thermodynamic framework is recommended to be used for your simulations. And this thermodynamic framework has been tailored specifically for upstream and oil and gas. So this is the one that we will focus on. And there are the other two, the AQ and MSc. MSc is preferred when you have, it's mostly, basically the solvent doesn't need to be water only. You can have other solvents, and it's preferred for most chemistries. And the AQ will be, let's say you have that your stream is more than 70% in the aqueous phase. So this will be a general rule to use the AQ framework. Okay, so let's get started. Let's go back to the software and we start creating our new, our examples. So let me just close this. I'm going to go to document 2 and I'm going to right click on it and close. I don't want to save any changes. I'm also going to close this file that I had as an example and this document 3. So we initially created this ScaleChem training day 1. So before we start any calculation, I want to that we set up our default settings in the software. So we all work under the same conditions, under the same units, under the same thermodynamic framework. So the first thing that we are going to do is we're going to click on these streams where you see these 3 drops of water. And let's double click on it to change the name. You have 3 options to change the name. You can double click on it. You can use the F2 key from your keyboard, or you can simply right click on it and then go to rename. Or actually there is a 4th option. You can just simply here go to the description tab and say and change the name there. So let's name that instead of streams, let's change it to ScaleChem. Did I say that right? Yes, ScaleChem training. That's the first thing. You'll see that now we changed that from streams to ScaleChem training. Select it again, and now let's go to our second step, which is go to the menu bar and select the chemistry tab and then go to model options. Okay, and then we click on model options. That will open up a new window where we are going to select the default thermodynamic framework for all the calculations. So the default at the moment, you'll see that it says aqueous. And that is not the one that we want to use for today. So we are going to click on it, and that will bring a list where you'll see the 3 different thermodynamic frameworks that I just previously talked about. And we are going to select the option MSc SRK. So click on it, and notice that now the MSc SRK framework was selected, and we should see under selected the MSc SRK and the MSc. Both of them work with the H3O plus ion or hydronium ion. That's different from the aqueous framework that works with the H plus ion. So once we do,
Diana?
sure. Yes.
Yes, sorry. Is that where you also, I know we're not going to touch on the corrosion solving issues, but just out of interest, is that where we select if we need to do a corrosion analyzer? Is that where we select the corrosion when we start opening our file, where I see corrosion MSc? Is that where you select for it now?
No.
Okay.
For the corrosion analyzer, it will be different. It will be first, the corrosion analyzer will work only with the AQ framework.
Okay.
And also for this MSc, this corrosion MSc, I will need to ask what adds this, but by default with the AQ framework, you just need to add an object that is called corrosion rates, and it will enable everything. It will turn everything on by default for you. Yeah, so you don't have to think about this parts in these chemistry model options.
Okay.
Okay, thank you for your question. Then let's click OK just to accept those changes. And now that we have done this part, let's make sure that all of us have the following units and the following naming. So for units, we go to the units manager where it says Celsius to Fahrenheit. That's the icon. And make sure that you have all of these default units that you have, for example, for my water analysis, that you have metric batch concentration. If we haven't moved them, all of them should be by default. Another one that we will be using, the brine analysis, would be metric batch concentration. We will be using the oil analysis, that will be metric batch mole fraction. Gas analysis, metric batch mole fraction. Scale scenario, scale metric flow and concentration. Again, if we haven't moved this previously, this should be by default. So I'm just going to accept the changes, okay? Or not changes, I'm going to just leave it as it was. And let's make sure that in our names manager, we have formula as the default. So what you see in my screen will be similar to what you see in your screen. And then click OK. Okay. So that is regarding how to set up our the thermodynamic framework. So anytime that we add an object, it will use the MSc SRK framework. Okay, so I just noticed that it's 9:52 and we haven't started with any calculation at the moment, which I don't like. We should at least start with a calculation within the first hour. But let's get just a quick break of 8 minutes, and then at 10 a.m. or at the top of the hour, we can start with our calculations. And if you have any questions, please let me know. But please go ahead and take a break, a short break, coffee break, and then I'll see you at the top of the hour in 8 minutes. Thank you.
Thank you.
Thank you.
Thank you.
Okay. Welcome back. I see AJ as well. Did you get some coffee, AJ? Whoever is back, please let me know. Just raise your hand or just say I'm here and state your name.
Good morning, Diana. I did, by the way.
I'm here, but I'm still waiting for the serial number to install the software.
Oh, that is.
My side went okay, so I'm setting the 4 units, something like that, on the software.
Yeah, back.
So was Greg that is still having issues trying to install the software?
That's me.
Oh.
Yeah, correct. I reached out to Jim, Diana, so I'm just waiting for him to see why there is an error in the download. It says invalid, so we're just trying to figure out what's wrong with it.
Oh, okay.
Yeah,
wow.
sorry, I also have the same error. I cannot
same issue.
download, yeah.
Mm.
Yeah, the same issue.
Oh, then let me add you to the conversation, Joel. If you can send me your email as well. For some reason, I don't have your email, Joel. If you can just send it in the chat over here, and I'll bring it to Jim as well.
Oh, I'm sorry you're having issues with that. I wonder what's going on with the serial number.
Okay, sorry, I was on mute. Let me send you my email.
Okay.
So I just have a question. Is it possible for 3 different people to actually to install the software with the same serial number? Because you have only given one serial number.
That's correct. That's the training serial number, and it can be shared. As long as you don't have if you have a licensed serial number on your computer installed already from the company, then it might be you might use it instead of downloading the training serial number. But if you haven't installed at all the software before in your machine, please feel free to share it and download it on your machine. Yes, it is shareable.
Okay.
Mm-hmm.
So
yes,
I thought that was probably a mistake.
Mm-hmm.
I only have the training software, so normally it should have been working for me.
Correct. Yeah.
Work.
And you've installed it and it worked fine with you, right?
Yeah, I installed, but now I just want to. I have the step where I have to enter my username and the serial number, and now I have the error message.
Okay. All right.
That's not good. Okay, we'll figure it out for you.
Yeah.
Sorry about that. Okay, so once we figure that out, and don't worry, we will be sharing I will be sharing the example files. But yes, hopefully that gets resolved by today.
We'll have the recording also, Diana, so we can pass that along to catch up.
Yeah.
So everyone should be hopefully able to catch up by Wednesday at the worst.
Right. Okay, so let's get started. We today are going to explore 2 different examples of OR calculations that we're going to be building in the software. The first type of calculation will be related to an aquifer production, well, similar to what I'm showing to the left, to study standard scaling during production. We will be covering basically chapters 2 and 6 of the manual because in these cases, what we want to know is if we are going to produce scale from the reservoir through the well and across the flow line into the facilities, and also study the effect of temperature and pressure on the scaling risk. The second type of calculation that we will be studying is the fluid compatibility, and this will be found in chapter 7 and 9. Probably, if we have some time at the end, we will be building it, or if not, first thing in the next class, we will be building this example. And this type of examples can be found, for example, in secondary or tertiary type of recovery. Okay, so let me just go to the next step. So the first case that we are going to create is called Olympus well. We will study the self-scaling of a moderate temperature, moderate pressure well with moderate salinity. So this Olympus well is going to be a gas well. There is no oil in it, and the water cut in the gas well is pretty high. This is just a basic vertical well, like I showed previously, that is producing gas and brine to a separator. We want to know if we are going to produce a scale from the reservoir through the well and across the flow line into the facilities. We have been given a water analysis. We have also been given a gas analysis and the production conditions as well. And we also know the flow rate of the brine, the flow rate of the gas, and we know the temperature and pressure of production. So how are we going to do this? We have all of this information. So how can we reconstruct using the software? So the first thing that we will start with is the brine analysis, which is highlighted here with this number 1. We will enter the composition of the water analysis. Then we will learn how to enter the composition of the gas analysis. The third step is to bring the water and the gas together to saturation using the saturator tool in the software to create a representative fluid at reservoir conditions. And then we are going to study the scale scenario to understand where we are going to have scaling risk of the fluid from the reservoir to the surface. We're going to do it by using a scaling scenario and a contour plot. And of course, we are going to learn how to interpret the results in each one of these type of calculations. So what is our main goal? To make a representative reservoir fluid from the available data. So we have our surface sampling. In this case was a brine and a gas analysis. Then we are going to back calculate what's happening at reservoir conditions. And once we have a representative reservoir fluid, then we are going to predict the scaling that is happening from reservoir up to the surface. Okay. So the first step that we are going to do is learn how to enter a brine analysis. So if you go to the actions panel, you'll see down here, you'll find the option that says add brine analysis. So once you find that in the actions panel, add brine analysis, then let's go and double click brine analysis. And this will create, yes?
Diane, I just want to pause you for a second. It's Mike. There was a question in the chat about oil wells versus gas wells. I presume.
Mike, I lost you. You're muted.
I hit it twice, unmuted and then muted myself.
Yes.
There was a question in the chat about oil wells versus gas wells, and I assume we're going to stick to the plan for the course, but I didn't know if you wanted to make any comments on if you would handle it differently.
Yes, we will cover the oil well as well. That will be my second example for today. So then, first what I want to do is to learn the mechanics of how to enter some basic brine analysis and gas analysis, and then we will go to a little bit more of complexity adding the oil well. Okay.
Okay, but so just to start with oil, because I mean maybe I'm mistaken or something, but we have a couple of oil wells in our assets, and going straight away to oil well will be for me useful, and we can directly figure out day-to-day issues. But I don't know what about other mates' point of view about that.
Sure. Yeah. Well, I mean, when we are going to do the example of oil well, we will have the same at the beginning, like more or less the same steps. But as I said, I just want to learn to teach the mechanics. We will do it. I'll show you here an example, my cheat sheet that I have. We'll create these objects for the gas well, and then we will go to the we can go to the other example that is Bacchus oil. It's another example that I have. So we can go through that. But I just want to start with the basic one, and then we will jump to that, if that's okay with you.
Okay.
Thank you. Okay. So the first example that I want to do is the brine analysis. This brine analysis has, okay, so in here you'll see that you have different ways of entering the water analysis. You'll have that you need to enter cations, anions, and neutrals. But before we start entering the data, what I want to do is to change the name of this brine. I'm going to name it, and if you double click on it, or you go to the description tab, then you can name it as Olympus brine. Okay, and then what I am going to do next is I'm just going to add a description here so that we know that this is a gas well. And then we will do an oil well after this. And then next step is to go to the design tab. And under the data entry tab is where we enter all of our water analysis data. Okay, so usually, probably, you will receive your analysis data in an Excel spreadsheet or maybe in a PDF with the information of your cations, your anions, and neutrals. And this is what we are going to enter in the software. So let me just start with sodium here. And let me just bring my cheat sheet here. So then it will be, for the sodium ion, we are going to say that that has 36,000 milligrams per liter. Potassium will be 300. For a calcium ion, it will be 600 milligrams per liter. Magnesium will be 150. Then we have some strontium in the water as well. That will be 80 milligrams per liter. Barium will be 5. No iron content. No iron content. For chlorides, so we go now for anions. Then we'll have that this concentration is 57,000. Sulfates will be 250. Then we'll have that the bicarbonate concentration is 600. And for neutrals, anything that is in a molecule type of state here, we have some silicon dioxide concentration of 15 milligrams per liter. Perfect. Okay. So now we have added this information here. I want you to notice the yellow column to the right. One is the value that we just entered, and then there is the balance column that is yellow. And what is happening here is that even before the software calculates any properties for this water, the software needs to make sure that the system is electrically neutral. So for this example, if you see in the summary table, for this example, the software is saying that there is a cation charge, a positive, this is a cation charge of 1.61, 77.6. And the anion charge is minus 1.6228. So what he's saying here is that we have a charge imbalance, a negative charge imbalance. So in this case, that means that we have more anions than cations, and that the amount of sodium that we need in order to make this water neutral is this amount that you see here, 116 milligrams per liter. Those sodium ions need to be added to the solution for this solution to be electrically neutral. And you'll see that this 116 milligrams per liter, if you go to the sodium component in the balance column, you'll see that the software have added the 116 milligrams of sodium here to balance this water. So why does the software do this? Again, this is because water is neutral and the software is reconciliating for this small deficiency that probably comes from measurement errors. So once you enter the data, then we go next to the Reconcile tab. Okay. So the purpose of the Reconcile tab is manifold. The first purpose is that in here you can enter the measure properties of the water. For this example, let's enter the measure properties that were reported. For this water, it was reported that the pH value was 7.67. Okay. And the alkalinity value was measured as 600 milligrams of bicarbonate per liter. Then the density value was measured to be 1.064. And there was a total dissolved solid as well. And total dissolved solid value that was around 96 to 80. Okay. Perfect. Let me know if I'm going too fast with this data entering. So that's the first purpose of this reconcile. We can enter the measure properties, and then the second purpose is that we need to select. We have the option to select how we can reconcile and how can we calculate the properties of this water. So you'll see this in this section. It says calculate brine properties using any of these options. So you have concentration data only, then you have gas-phase CO2 content, measure pH and alkalinity, measure pH only, and measure pH, alkalinity, and TIC values. At the moment, I want to start with the basic one, which is the concentration data only, and I will expand later on these other options that you see in this section here. So if you select concentration data only, then we can go ahead and calculate the properties of this water. And the reason why I usually select this concentration data only option is because I want to compare the measured values versus the calculated values. And I want to see how these calculated values are, if these calculated values are far away from the measured or if they are more or less similar. So for example, our calculated pH is 7.52. This pH is about 0.15 units below the measured value. So the question then is, should we adjust the acid or the base concentration in this system in order to match the measured pH value? What about, yes?
As a rule of thumb, which deviation do you allow in terms of measure versus calculated data?
That will be a user preference. I don't know if you, some users they just want to make sure that they match the pH. Some other ones will see these results and they will say, it's good enough. Okay. So it will depend of the user preference. Okay. But I would say a 0.15 unit, you would need to see how much that impacts the scale formation. You could do that study as well. Okay. Mm-hmm. Yes, so what about the alkalinity? So it was measured 600 and the software is saying that that is based on the concentration that we enter only, that this calculated alkalinity is 20 milligrams lower than the measured value. So the question here would be, again, the user will decide do we add more bicarbonate to the system to match the measured value, or we just leave it as it is. So for my example, I'm not going to pursue this. I will just say these calculations are close enough. And I will just use this water analysis to continue with my example. But again, if you want to do to match the alkalinity value or to match the pH, so those will be these options that you see here. For example, it says measure pH and alkalinity. You would select that option to match both pH and alkalinity value. Mm-hmm. So these different options up here also, it will have an impact because what it's saying is that it's providing some ways to modify the fluid chemistry, and that you will slightly be modifying the chemistry if you use these options here. But I will talk about that later in one of my examples that I have. So any questions at the moment regarding this? If not, I can go to the next slide, where we are going to analyze the report. So now that we have calculated this, if we selected the calculate button, let's run it again just in case I forgot to say calculate. So
Diana,
yes?
This is this is Ezekiel. Well, this is calculating. Somebody asked the question, will it adjust the Na plus every time to sodium every time, or will it adjust others as well?
Right. So let me go back to the data entry option. So it depends. It depends of the balance options. So there are different balance options. And for this case, the software has selected the dominant ion. What that means is that the software will come through these values, the cation values, and see which one is the highest. So in this case, it was sodium plus. For the anions, it will do the same scan. It will say which one is the highest anion in these values. So that will be the chlorine. So because we selected the option dominant ion, so it will select the deficient one, but it will select the one that is dominant either in the cation section or in the anion section. If you don't want to select the dominant ion option, the software allows to do some other balance options. It will be the prorate cation, the prorate anion, and the makeup ion. So what do they mean? So let's say for makeup ion, you say, no, I don't want that the software select the sodium ion. I think that we can do the makeup, or we can do the electroneutrality with potassium cation or the potassium ion. So you can select it, and you'll see that the software immediately did the balancing option. So you'll see that instead of 300, now your new value of potassium will be 497.2 milligrams per liter. And you'll see to the right as well, that's what it needed to be added, 197.2 milligrams per liter to reach that electroneutrality value. By default, I just selected the sodium. If you selected sodium as the makeup ion or the dominant ion, the calculations will be the same. And what about prorate cation and prorate anion? So what this means is that the software will just increase the concentration. Let's say you select the prorate cation. So you notice to the right that what it's doing is that the software is still keeping the same ratio of these cations, but it's increasing the values in order to reach electroneutrality. And to the right, you will see what were the modifications, how much of sodium was added, how much of potassium was added, calcium was added in order to reach that electroneutrality. So you have all of these options within the software to reach electroneutrality for your solution. So let me go back to the dominant ion. And let's make sure that we all have the same selection, dominant ion, so that we can see the same results of our calculation. And I have to recalculate again because I made some changes there. And once we recalculate these values, then the next step is that we are going to go to the report tab and analyze the results. I hope that I answered the question.
That was very thorough. Thank you, Diana.
Okay, good. So in this report tab, you will see different tables. And the first table that you will see here is the stream properties table, which will tell us the conditions at which the calculations were, the measurements and the calculations were performed. So it was 25 degrees and 1 atmosphere, standard conditions. Then we have the phase properties table. what I like to see from this phase properties table is the pH, for example. So it is saying, we already saw that as well, the pH was 7.52, slightly lower compared to the measured value. You will also see the calculated density and other properties such as the specific electrical conductivity and an alkalinity value that is being calculated based on the data that we entered. The other table that probably we are very interested on today is the pre and post scaling tendencies. And as we calculate scaling tendencies for this specific example, you'll see that there are 1, 2, 3, 4 different values. You will see pre-scaling tendencies, pre-index, post-scaling tendencies, and post-index. Okay, so I want to explain each one of these. I want to give you the definitions of what we mean by pre-scaling. What do we mean by pre-index? What do we mean by post-scaling tendency? So one overall thing that I want to mention here is that when we are saying pre-scaling tendencies or pre-index, it means that we are calculating the scaling tendencies before any solids have precipitated out. What we mean by post is we have calculated the scaling tendencies after solids have precipitated out. So let me go back, let me go to the slides. And in here, this is the general definition of the scaling tendency values. Scaling tendency is calculated as the ratio of the ion activity product to the solubility constant product. This value basically indicates how close a mineral is to saturation. Hence, this definition of a scaling tendency is essentially calculating saturation ratios. Okay, so whenever your saturation ratio is below 1, that indicates subsaturation, and no solid or mineral is expected to form. If the saturation ratio or scaling tendency is equal to 1, that indicates saturation. And that means that if a solid is formed, well, because we have a saturation there, means that the solid formed, and that solid is in equilibrium with water. The other result that you could see is that scaling tendency is above 1, and that indicates supersaturation, and that will indicate that solids will form. Now, as I previously mentioned, there are 2 values that that OLI software reports for scaling tendencies, depending on the scenario that we have. We saw that in the report we had a pre-scaling tendency value and we had a post-scaling tendency value. To the left, I am trying to show you how the pre-scaling tendency is visualized. This pre-scaling tendency value is basically the saturation value that is calculated before any solids or minerals precipitate out. This value basically assumes that you have all of these ions suspended in solution. They are all dissolved, and you'll see that there is no solid formation. You could see this system as a system that is time equals to 0 and has not reached equilibrium. Basically, you just have it suspended, and you just put these salts in solution, and you have them all suspended. There is no time for them to precipitate out, to be precipitated out. So, as a quick note, for example, this could be seen, like for example, when you have a water analysis. When you have a water analysis, it is assumed that solids do not precipitate. And why is that? It's because these water analyses, they are usually acidified or they have been digested in acid. Thus, everything must remain in solution to do the respective analysis through ICP. So that will be that pre-scaling tendency scenario. What about the post-scaling tendency value? This post-scaling tendency is the saturation value that is calculated after all solids or potential minerals have formed and are in equilibrium with water. This is the true equilibrium condition, where time is equal to infinite, or time goes to infinite. Okay, now the software also shows two other different values. It will be the scaling index. The scaling index value is defined as the log 10 of the scaling tendency. So we saw that we had the pre-index and the post-index. So similar to the scaling tendency, if the scaling index is below 0, the solution is subsaturated. If the scaling index is equal to 0, the basically means that we have it indicates saturation, and again the solid is in equilibrium with water. And if the scaling tendency is above 1, then above 0, then you have that the solution is supersaturated. Okay, so let me go back to the software, and then we can start analyzing the results that we got for our pre-scaling tendencies and for our post-scaling tendencies. And let me check my chat window if I am missing some questions. Okay, no. Okay, so let's go to the pre-scaling values. Let's look for any value that is greater than 1 or similar to 1 or close to 1. So let's see here. So you'll see that barite is 7.6 or 7.7. You have calcite 6, and then you will see down here strontianite 2.6. All of these values are above 1, and all these values are indicating that these minerals are all supersaturated. Okay, and of course, if you go to the pre-index, then you will see that they are above 0, right? Because it's a log scale of this value. So it is quite possible that if we let this sample in the lab for an extended period of time, we will start seeing a precipitate at the bottom of the container. But in our case, we have told the software that no solids are allowed to form. So we are assuming that all of these cations and anions will remain in solution. Down below, we'll see the last table that we have. This is the brine composition. Okay, and in this brine composition, in here you'll see a summary of the data that we enter in our water analysis. So you will see the value of anions, cations, and also your neutrals. As a side note here, so I previously mentioned the solids are turned off, everything is assumed to remain in solution. But let's say that you want to override that assumption, that no solids, that you don't want to let it as no solids precipitate. Instead, you want that to allow solids to precipitate. So you have two different options. One option is to turn on the solids here, the button that says SO, or the other option is to go back to the design tab and select the option allow solids to form by checking that and then rerun the calculation. But at the moment, I will keep it as it is. I will just leave everything as everything is suspended in solution, and we will move to our second analysis, which is the gas analysis. And I hope that you have any questions? Yes.
Yeah, put your hands up. I have a question, please. Dennis is talking.
Yes.
Maybe I'm something, but I would like you to remind me why everything will be kept in solution and not solely be precipitate.
Yes, because the reason why I'm leaving them in solution is to recreate the worst case scenario. So if you allow some solids to precipitate, then you don't have as many cations in solution, and probably you will underpredict the solid formation. And I just want to assume the worst case scenario for this example.
Okay, so it's an example, and you are the one, the user, which is allowing solid to precipitate. That's what you are saying for this example?
For this example, we are not precipitating. We will leave the solids off. So everything remains in solution.
Okay.
Yeah.
Thought it was because of type or pre-index or pre-scaling factors or value, but okay.
Yeah, I mean, they are very high. And I just want to, with these values of barite and calcite, and they're super saturated, I don't want them to precipitate at the moment, because what I want to make sure that I bring this to reservoir conditions, and I want to predict the worst case scenario for the whole production line.
So in a normal life, based on pre-scaling value of barite, calcite, they should normally precipitate. That's what you are saying. But on the software, you will prohibit it. Okay.
For this example, this based on this water analysis is saying that barite, calcite, and strontianite will precipitate because they are super saturated.
Okay. Yeah. Okay, good.
Great. Thank you for your question.
Thank
Yes.
you.
So next example is the gas analysis, and this one is very simple. This doesn't really require a lot of thinking or interpretation. We just need to go to the actions panel, and we are going to click on the option Add Gas Analysis. And that will create a second object under the ScaleChem training, and we are going to double click it and change the name to Olympus Gas. So again, this is a straightforward object. It contains, you'll see, simple hydrocarbons. You can see that all of these are alkanes, and you see that you have hexane down here. And by default, the software selects methane as the makeup gas to normalize the total composition to 100%, 100 mole percent. And there are different normalization options here. You'll see the makeup and also the prorate. At the moment, I will just use the makeup option to normalize the gas analysis. So let me enter the data for the gas analysis. And what I'm going to do for next class is I'm going to give you an Excel spreadsheet so we can just copy and paste. But at the moment, I want you to get comfortable how to enter data here. So let's start doing the data entering here. So we are going to start with water, that's 1.8 mole percent. Then we have nitrogen, 3%, CO2, 1.5%. This gas well has a H2S content of 0.5%. Methane is 65.5%. Ethane, 14%. Propane, 8%. Isobutane, 1%. And butane, 3%. Isopentane, 0.5%. This is normal pentane, this is 0.7, and finally we have the hexane, which is 0.5%. So you'll see that you have your values and then normalized. So in case, for example,
Diana,
yes?
If you do have more components into your gas, how do you add them?
Yes, so you'll see
okay.
Here, you just type, let's say you have heptane, and you just add it.
Okay, thank you.
No problem. Okay, there is another thing I want to show, maybe now that you asked that question, is you'll see the template manager to the right, it says standard. What we just entered here was the standard template. This is the basic short template. But if you wanted to use the expanded template, so it will increase even more. So you will have heptane, or you will use isooctane, nonane, and also the decane here. But again, you can always add more components. And if you, let's say you even have more components here, you can always save that template. So you will go to Save As, and you will give that name to your new template. I don't know, it could be my template of gases. My gas template, for example. You can save it, and Later in another calculation you want, you just bring my gas template, and then you don't have to enter the same components over and over again. But I will leave the standard at the moment. And these are the composition. This is the composition. To the right is the normalized section, and you'll see that there are no changes here in the normalized composition. Then you'll go to the reconcile tab, the blue tab. And what we're going to do here is we're going to press the calculate button. Okay. Notice that the standard conditions for this gas analysis will be 50.5 degrees C, 15.5 degrees C, and 1 bar, basically here. And notice one thing in this summary section to the right. It's saying that you have two different phases. You have a small amount of liquid or aqueous phase, okay? And you have a vapor phase of 99.5 moles, okay? That's because what happened is that when we enter the composition of this gas, we enter a slightly higher water content. This was 1.8% of water in the gas in our gas analysis, but this value is slightly higher, and that means that the gas is saturated with water, and the maximum amount of water that that gas can hold is 1.75 mole %. And that's why the extra amount of water that we enter here, you'll see it as a liquid phase or an aqueous phase at 0.05 moles. Also notice down here that the aqueous phase, the pH of that aqueous phase is around 4.8. And it is important to know this pH of this condensate because this pH is very low, and probably is due to the fact that we have CO2 in our composition, and we also have some H2S content. And these gases will dissolve in the water phase, and these acid gases will contribute to the acidity of the water. That's why you probably are seeing this pH value of 4.8 for the condensate, the condensate that is being created in this gas analysis. Okay, so that's all the steps for the gas analysis. And next, what we're going to do is to recreate the reservoir conditions. So at the moment, we created a brine, a representative brine. We have a representative gas. And now we are going to bring those samples back to reservoir conditions. That's what we are going to do in our next object. So that object is called the saturator object. So I'm going to go back to the software, and we are going to go to the actions panel, and we are going to select the add saturator object. In this saturator object, so double click on it and label it Olympus reservoir. Okay, and this Olympus reservoir, we need now to specify the inlets for this Olympus reservoir. So what we're going to do is go to the inlets tab, and under the type column, we are going to select the option brine. Okay, and then immediately the software knows which brine we have previously created. That is the Olympus brine, and we are using the MSC SRK framework for that brine. So we select Olympus brine, and we also need to define the amount of flow. So basically this will be the production rate that you are entering here. That value, we can put it as 200 cubic meters per day, because that's the units that we have defined, cubic meters per day. That's 200 cubic meters per day of brine. The next one that we need to include here is the gas. So we'll go under type, select the gas option. The name will be the name of the gas that we just created. Olympus gas. And the flow rate of this gas is going to be 250,000 standard cubic meters per day. Notice that the units of this gas is a standard E3, that stands for 1,000 cubic meters per day. So we are going to enter in the underflow. We just need to enter 250. We will suppress the zeros because this E3 is basically accounted for the 1,000. So we have 250,000 standard cubic meters per day. Okay, so that is regarding the inlets. Now you need to go back, you need to go down here to conditions, the conditions grid. In here is where you define the temperature and pressure at whatever temperature and pressure that you want to saturate these two fluids. In our case, we want to simulate the reservoir conditions. So what we will enter here is the reservoir conditions that we were given, that is 125 degrees C. And regarding the pressure, that will be 275 bar. Good.
Sorry, Diana.
Sure, go ahead.
Yeah. If I want to change the gas value to ScFD, I go to metrics or?
So you have two options. You can just click on this hyperlink.
Okay.
And that will open your Unix manager. And you want to change it to
ScFD.
This one, right? Or no? You have different options here. Standard, so you have the standard cubic meter. You have the standard feet.
Yes, that's the cubic feet. That's the cubic foot. FT3 is the FT3 is a cubic feet. So
cubic feet.
Yeah. Okay.
So the other you can spell it MMSCF or FT3. That is the same.
Yeah. You have the option to change. At the moment, just because I was using the metric, maybe next time I'll use, I don't know which one to use. Sometimes I use the English, so they will use the cubic feet. Sometimes I use a metric. So I don't know which one is best to use for training. I tried to make it like general, so that's why I selected the cubic meter. Maybe for next training, I will use the English units. Which ones do you use normally? The cubic feet?
The cubic feet, yeah.
Okay, so I will keep that in mind for next training. But at the moment, I mean, you could, if we change it, then, no, I just want that everybody gets the same result so that we don't get confused.
No problem. You can leave it. You can leave it like it is.
Yeah, but
you
you have the option.
No problem. Yeah, you have the option.
Have the option. The other option I want to, now that we're talking about units, is you can always go to Tools and Units Manager. And if you go to customize, let me cancel this. If you select this, the global stream, this global stream here is ScaleChem training, then you can go to Tools, Units Manager. That was fast. Tools, Units Manager. And in here you can select, let's say you have the gas analysis. So you can change it to English, you can change it to SI units. You can always customize if you want it as a feed, the cubic feet, etc. So you have those options to customize your specific icon or your specific calculation. But yeah. Okay. So next time I'll use the standard, the cubic feeters, the cubic feet. But at the moment, I stick with metric. And we have 250,000 cubic meters per day. Okay. And for temperature and pressure, I also I'm using temperature degrees C and 275 bar for pressure. Perfect. The next step, once we define all of these flows and the conditions for saturation, then we'll go to the solid tab, which is this blue tab here. What I want what I want to do in this tab is to select which solids may or not may precipitate or may not precipitate or form in the system. So you will have two options in this tab, in this solid tab. You have a first section that is called the solid selection section, and you also have the reservoir mineral saturation section. So I will start first with my first section here, and then later in the class we will learn how to use the reservoir mineral saturation. So this solid selection section has three different categories. It has the standard category, which basically is listing all the standard oil and gas scales that can form. The minerals that show that you see here in this standard list is going to depend on the elements that you enter in your brine analysis. For example, in our brine analysis, we didn't enter any iron content, so we don't have anything related to iron content in here. But if you had it, you will see a component that may form containing iron in that composition in your brine analysis, or in your brine analysis. Okay, then you will have the expanded category. And this expanded category, you will see solids that may form when you have unique compositions. For example, let's say you're modeling a completing fluid. And so that's why you will see here that you have calcium chloride. Or maybe you're doing a flooding application where you can precipitate magnesium hydroxide. So you will see it here, magnesium hydroxide. Or some other type of different mineral that normally is not found in the standard category, you will find it in the expanded category. And then you will see the all category. It's basically these solids. This list is showing all the solids that may form when solids that may form and are present in the OLI database. So you have all of these possible compositions. You have chlorides, calcium, sodium, sulfate. So these are all the possible solids that we have in our database, and they will appear here, okay, in this all section. And again, it will depend on the chemistry that you have or that you have previously entered in the software. So if you don't see it in the standard, you may go to the expanded or to the all solid to select the solids that you want to use to allow to form or to precipitate in this calculation. Okay, so for this calculation, we are not going to select any option here, and I don't want to select it yet. The reason why is because I want to see what happens before and after we let the solids to precipitate out. So what we're going to do here is go ahead and calculate. Just click on the calculate button. And notice that that button was yellow. And this means that you can still calculate, but the software is telling you that there is a warning. There is a potential problem with this simulation. You'll see that in this case, we have a warning that is purple and it's saying you didn't select any solids for this calculation. And that's right. We did not select them. And the reason is because, again, I want you to see the results before saturation and after saturation with solids. So now that the calculation is done, so let's go to the report tab. Okay. So what are we going to see in the, this is what we do, well, this is for saturation, so no, this is not the step I want to do. Okay.
Excuse me.
Yes.
So the calculation button will still remain yellow. That's it, right? Because of the warning.
Right. And I did it on purpose because I haven't selected any solids. In this step, it is expected to select solids, and I didn't. Because, because we're going to presume that we don't need any minerals to saturate the reservoir. We want to find out first what are the saturation ratios of the minerals at reservoir conditions, just with the analysis that we entered. Then we will see how is the behavior without allowing any solids to precipitate out. And then we will put the solids and see what happens. I just want to see the without solids and with solids. And because this step is expected to see solids precipitate, or in here you need to select solids, so that's why you're seeing the warning. However, if it's yellow, it's still the calculation runs. It will run. If the calculate button were red, it will not let you to do the calculation.
Okay.
Okay.
So, Diana, if I'm trying to understand what we're doing here, we are trying to calibrate the model versus the measure data that we already have. So I believe we have a base which is the field conditions. Based on this field condition, we now want to evaluate, or let's say calculate what is the output based on the input.
Right.
But to do this, we need to calibrate the model basically to the field conditions. So what I mean is you have a basis. Let's say I receive data from the lab chemistry, okay, in my plant.
Right. Mm-hmm.
In this lab chemistry data, I will have all the different components with possibly with the mineral that are precipitated as well. But as I'm calibrating the model, I will ignore the solid formation tool to see how the model that I'm trying to build is close to the field condition, and then add the solid to now benchmark my model, which I will now be using based on the deviation that I allow to myself as the user for now evaluating, or let's say predicting what is the scale formation. Is that correct? Is that
yes? What you just said is correct. So
okay.
Based on the what we have so far, we want to understand. What are the results we get, just as they are, without any solid. We want to understand what will be the saturation ratios if we are close to saturation, if we're not. And first we want to understand that scenario, then we can go back and say, okay, we can saturate with cemented material like calcite, barite, etc. And we can understand the changes that were done on the composition of that base case. Okay, so yes,
thank you.
That's correct. Thank you for that summary. Perfect. So what we are going to do next is to go to the report tab after the calculation. So notice one thing, every time that you do a calculation, you'll see this check mark, this green check mark, meaning it's completed. So the first thing that I want to show you here is to show you the inlets summary table. Okay, and in here you will see the overall mass balance in our, or the mass balance of this reservoir for the brine and for the gas. This will be the mass that you have at the conditions of the reservoir. Then the next table is the stream properties. And you also see the total mass that is being produced. And this would be around 466,000 kilograms per day of material. Okay, then you'll see the table that is called phase properties. And these properties are basically the properties that we will that were calculated at reservoir conditions. So for example, the aqueous phase has a pH of 5.6. You'll see down here also the mass or the moles of each phases. So for example, for the liquid phase, we have around 214,000 kilograms in the liquid phase, and we have the 252,000 kilograms in the vapor phase. You'll also see the densities down here that were calculated for each phase. And down here in the gray row, you'll see the volume that is also calculated, or the volume that is being produced on a given day. So you can see that there are around 210 cubic meters per day of brine flowing through the perforations. And regarding the gas, you have around 1,180 cubic meters per day of compressed gas flowing through the perforations. This is at the reservoir conditions. This volume units is given at reservoir conditions. When we are talking about the decompressed conditions or the standard conditions, these are the flow rates down here. So this will be the volume at the standard conditions. And you can see, for example, that for the gas phase, that gas phase has increased by a factor of more than 200 times. So because now we have decompressed that gas at standard conditions. Okay, so then we have the pre and post scaling tendencies table. So what I want to focus on is the results that we are obtaining at the pre-scale values, or these, the pre-scale values results. Oops, these ones here. So look for any values that are above or close to 1. That means that we are close to saturation. Okay. So what do we have here? We have that, for example, calcite here. We have it is around 63% saturated. We have barite, it's around 84% saturated. And I don't see any other values. Let's see that everything is below, like considerably lower than 0.8 or 0.6. So all of those minerals are substantially subsaturated. So with these initial results, what it means is that it's possible that barite or calcite would be at equilibrium in the reservoir. And this is because the measured values were brought down to reservoir conditions and are close to saturation. Is there any question? Okay. So, no. All of these results were calculated with no solids in the tab. If you remember, we didn't select any solids. So, and in fact, for this case, if you see to the right, if you see here, let me just go back. In fact, for this case, solids would not form because if you go to the pre-scaling tendency, nothing is above 1 or equal to 1. So we will not even form any solids because based on this analysis, we are not close to saturation. So in our next tasks, what we are going to do is to allow solids to precipitate. Okay, so I'm going to go back to the design tab, and it's also notice that it's the top of the hour. So what I'm going to do is I'm going to give around 6 minutes of break. So I will see you back at 11:08 or 8 minutes past the hour. Okay, so just go for some stretch and some coffee, and I'll see you in 8 minutes. Thank you.
Okay, thanks.
Okay, thanks.
Hello, hello.
Hi, Diana.
Hello. Okay, so let me know. You could raise your hand and just state your name that you're back. Hello, Dennis is here. Okay.
Hello.
Hello, I'm back.
Great. Mike, what is the what AJ he likes to say about that?
AJ always asks for anyone who's not here to raise their hand or let us know that you're you're
please
not.
let me know. Yeah.
There you go. Yeah.
Please let me know. I like that one. Great. I like the option of raising the hand of Teams. It's much better than the one at WebEx. It's more obvious. I like it. Okay, thank you for being back. We will finish this case and then we'll go to our second example because we have a lot of topics to cover. So, but it's good that you're having questions, and let me know if you have any questions too. If anything, if I'm going too fast, let me know. Okay. So we were saying that we did this calculation without any solids, and we found that barite and calcite, they were near saturation, 70%, 60% is near saturation, but really nothing was predicted to precipitate out. Now what we are going to say is that we are going to assume that there is this reservoir fluid is in contact with a rock matrix. And if we know the mineralogy of the rock matrix, the fluid will be near or at saturation with those minerals. So let's say, for example, that this is a sandstone reservoir, and the cementing materials include barite and calcite. Now that we know this, we can go ahead and turn on the standard solids box. So we will just check these standard solids. And what this means is that all of these standard minerals are allowed to form if, and only if, they are supersaturated. Okay. So this step just allows us to select all the possible solids that we could form. That's what we just see here. Now, the next step is to go to the reservoir mineral saturation section. Okay. In here, we can explicitly, we are going to tell the software that barite or barium sulfide is present as part of the cementation material. Therefore, I want that the software saturates the water and gas with barite. Okay, so let's add barite down here in the mineral, in this mineral to saturate column. So if you click on the white row in here in the white section, you'll see that now you have a drop-down arrow here. So what you're going to do is click on it and select the option barite. So just click for, this is the first option here. So just click on it. The next step is to click on this yellow in this yellow row. That means immediately we'll bring barite as an inflow to vary. Okay, so we select the barite and then we click on the yellow cell just to make sure that the software automatically fills this up for us. So what this means is that in order to saturate, the software will need to add or remove barium and sulfate ions from the water until barite becomes saturated in the water. Okay, that is with barite. Now, what about calcite cementation? So we will need to instruct the software as well that we want to saturate the water with calcite. So what we're going to do is click again on select solid and use the drop-down arrow and select the first option in this list, that is calcite, and then click on the yellow section. Okay, so that means that the software is going to adjust calcium ions and carbonate ions simultaneously in order to reach saturation. So we need, why am I saying barium and sulfate and calcium and carbonate, and yet I am still seeing this as a molecular input? the reason why we need to do this adjustment in a molecular input rather than just selecting sulfate or barium or calcium ions is because the software needs to do this adjustment in a neutral basis. I just can't add calcium or carbonate ions separately because we need to keep the system electrically neutral. And that's why we are adding barite or barium sulfate and calcium carbonate.
Diana?
Yes?
Let's say while I'm working, I want to remove one of the component at this time. Let's say I want to remove calcite. I don't want to use it anymore. How do I delete it from the drop-down menu?
You don't want to saturate it, right?
No, let's say I'm selecting my component, all of them, but then I decide out of all the component that I selected, I'm just removing calcite, for example. How will I delete calcite from the list?
So let's say I don't want this anhydride that I just added here. So I just select it and use the delete button in the keyboard.
Okay.
And then enter. And then that's how you delete it.
Okay, thank you. Easy as that. Okay, thanks.
No problem, yeah. Right, so now that we have defined that both of these minerals will be saturated in the water phase, now we can go ahead and click on the calculate button, okay? Perfect. So I don't know if you noticed, but now in this case, the calculate button was green. And the reason why is because we are satisfying all the requirements needed to define this object, which is selecting the solids and saturated. We're also saturating fluids with minerals. Okay, so the next step is to go to the report. And now we are going to analyze the results. Okay, so that's our next step. We are going to analyze the following tables where we want to understand the saturation details and also the scaling tendencies. Okay, so in this report, the first table will be saturation details. Okay, these first two columns that you see here are basically summarizing which minerals the software used to saturate the fluid with. And also you'll see the respective inflows that we adjusted, which is the barite and calcite. So these are the minerals and these are the inflows that were adjusted. The third and fourth column that you see here represent the concentration of barite and calcite in the system before saturation and after saturation. And before adjustments were performed and after adjustments were performed. And then you'll see a fifth column that represents the difference between the final and the initial values and tell us how much barite and how much calcite were added to the water or removed from the water. In case you see a negative sign in here, sometimes you will see that. That means that it was removed. In this case, we are not seeing negative values. We're seeing positive values, meaning that we have added barite and calcite to reach saturation. Okay, so in this case, the software added 1.49 milligrams of barite and has added 102.4 milligrams of calcite. Now, because we are adding these inflows to my analysis, then it means that my initial brine analysis will be slightly modified. So we will see that in our brine analysis report. So if we scroll down, you'll find a table that says brine composition. Okay, so in here you will be able to see to compare what was the original barium concentration. If I remember, I think it was around 5 milligrams per liter, but now we have modified it and by adding barium sulfate. So now we have that the barium concentration is 5.6. We will also see changes in the calcium. I think it was 600. Now it's 610. And so on. So the bicarbonate concentration will change. because we changed the carbonate concentration with the calcium carbonate and so on. So those changes also reflected in this brine composition. But let me go up here again, and let's start with our phase properties table. I want you to notice the pH of the liquid or aqueous phase is now 5.71. It didn't change very much. And the rest of the properties really didn't change very much either. You don't see like a lot of significant changes. One change that now you see, or an extra column that now you see, is a solid column to the right. You'll see that now the software is reporting a very small amount of solids for either in mass or in moles, and it's a very small amount of solids of around 8 times 10 to the minus 6 kilograms per day. And why do we see that solid column in there? It's just because we have instructed the software to saturate the reservoir fluid with minerals. But in order to perform that saturation, we just need to make the software to predict a small, tiny amount of solids to reach that saturation. Okay. Now, if we go down here to the pre-scale and post-scaling tendencies, and if we focus only on this pre-scale value here, now you will see that barite, the scaling tendency of barite is equal to 1, and also the scaling tendency of calcite is equal to 1. Okay. Now, basically what you'll see is that because we instructed the software to saturate this fluid, now the saturation, the scaling tendency is equal to 1, or the saturation ratio is equal to 1. This is because we have instructed the software to do this. So now with these results, we can say that we have created a representative reservoir fluid that we said that is going to be saturated with these two minerals. So once we're confident that let's say we're sure that this is a very good representation of the fluid, we can go ahead to the next step, and the next step is to calculate the scaling risk as we are producing the well. And how do we do that? How do we start creating, how do we predict the scaling risk during production? We are going to use what we call the scaling scenario object. Okay, so to do that, I'm going to go back to the actions panel here. And you'll see that we've done the brine analysis, gas analysis, saturator, and the next object is the scale scenario. Double click on it, and let's change the name to Olympus Production. So, what's the name? Olympus. My typing skills today are very slow. I don't know why. Okay, the purpose of this object is to study the effect of temperature and pressure on the properties of this reservoir fluid that we just created. We said, okay, this is a representative fluid. Now I want to see what happens to the scaling risk. Does it increase? Does it increase as a function of temperature and pressure at different locations during production? So you'll see 3 different tabs. You have the inlets tab, the conditions tab, and the solids tab. The inlets tab is where we need to specify the fluid that we want to study. This is very similar to the saturator object, and where you have to specify type, name, and flow. In this case, what we're going to do is we're going to say that we want to use the Olympus reservoir rather than the separate Olympus brine and Olympus gas. So what we're going to do is we're going to say, the type of fluid is the whole fluid, okay? And the whole fluid, that means that it's going to be the combination or all the contents of this Olympus reservoir. Then the name will be Olympus reservoir, and the flow, I will leave it automatic. So again, what we have done here is that we have taken the multi-phase flow of Olympus Reservoir, and automatically we are including all the mass in here, all the mass that we already entered or defined in the Olympus Reservoir or in this saturator object. Okay, so that is how we selected or we put the inlets for this Olympus production. Now, at this point, we can say that we have a mass balance between the saturator object and the scaling scenario object. Again, because we are bringing automatically all the contents or the flow amounts in the Olympus production. Okay, the next step is to go to the conditions tab. We're going to click on the blue tab, conditions. And what do we do here? In here, we are going to set the production locations. So under the location column is where you'll see that there is a drop-down arrow here. And here is where you're going to click to select the name of, I don't know, the locations that you want to study. So let's say, for example, that in here, we're going to say that our first location is going to be the reservoir. So just scroll down until I find the option reservoir. Okay. And then after I enter the reservoir, then I enter the temperature and pressure conditions. So let me just bring my cheat sheet here. I don't remember this. There are so many locations. So I'm going to say that that reservoir is going to be to 125 degrees C and 275 bar. Then we'll say that the fluid then is going to go next to our bottom hole. So I click on the drop-down arrow and go to bottom hole and enter the conditions, 125, 260. The next location is going to be downhole. And the conditions for downhole is 115 and 190 bar. Next time we'll do this by copy and paste it. Yes?
Since we enter those information about reservoir, both reservoir temperature and pressure on the Olympus reservoir, and since that we call back reservoir properties, why the software cannot automatically call also the 125 temperature degrees Celsius and 275 bar of pressure?
Oh, that's a good point. I wonder, maybe because it doesn't automatically knows that we are talking about this reservoir here, this Olympus reservoir. But that's a good point. We should, yeah, I will.
Yeah, we should link, like allow to use Olympus reservoir on those on this list.
Yeah, the only way, the only place where we are doing that is in the inlets. But because this part in here in the conditions, it doesn't assume that we will put the reservoir again. Probably that's why the option is not there. But I just like to start from reservoir so we can see what were our initial conditions and then how it changes as we change different locations. Yeah, that's a good point.
To add it, to allow the user to choose that. Yeah, we are not talking about another reservoir, but we are talking about the Olympus reservoir.
Yeah. Yeah, I'll bring that to the developers. That's a good point. Thank you so much for that insight. Okay. No problem. Thank you. Yes, so let's add, I think we have four more locations. So let me enter the next one. It's downhole. Next time I'll just send you Excel spreadsheet where we just can copy and paste and save time. But at the moment, again, we just need to learn and be familiar how to enter this data. So for me, well, we have 105 and 130. The next one is wellhead. The conditions are 100 C and 100 bar. And finally, the one before the last one is the choke. So we have choke. And then we have that the temperature is 90. So you can see how the temperature and pressure starts to decrease. And finally, we have the separator where we did all of our measurements, right? The brine, the water analysis, and probably the gas analysis as well. That was at 60 degrees C and a temperature, a pressure of 30. Okay, so let me know if you were able to enter all of this information. I'm double checking. We have the same result, the same values as I did before. Okay, okay. So then you'll see down here, you enter here the locations, and down here in this section, okay, you'll see now that you have a flow here with the different locations. And you will see the name of the location with the respective conditions. And based on this diagram, you can see that all the material is being sent through, right, to the system. And you'll see that we'll have the same mass everywhere. We are not assuming that we are separating mass anywhere. We're just assuming that the mass balance is conserved, that nothing is lost or separated, okay? The next tab is to go to the solids tab. So we click on it. And we are familiar now with this section. And here is where we are going to select the solids that we will allow to form the standard solids that can form in this for this reservoir fluid. So by common practice, in the majority of cases, is to turn these standard solids on. And turning these solids on means that if any of the minerals become supersaturated, they will be allowed to precipitate. Okay, so then the next step is to calculate. Press calculate button. And the next, how are we going to analyze the results? That would be using our plot and table capabilities that we have in the software. Perfect. So once the calculation is done, then click on the, you'll see up here, there is some tabs. Go to the plot tab. And in here you will see some preliminary results. At this moment, we should save. And please use the save button to save everything we have done so far. And I don't know why I haven't instructed the saving before, because we don't want to lose anything. So just make sure to save using the save button or file save or Control S.
Sorry, I'm not getting the same result. It seems like my in the conditions, my route has been changed. For some reason, I selected calculated, and then on the locations for in my condition, everything has been interchanged. Now it's starting from separator, choke, wellhead, mid well, downhole, bottom hole, reservoir. From top to bottom. Yeah, so and indeed my results are just the opposite of what you're getting basically.
Yeah, maybe what happened is maybe you sort by temperature or pressure. So what's happening, probably you did temperature, I don't know, something like this. So it will change. It will put separator, choke, wellhead, you know, because it's sorting from the lowest to the highest.
Okay.
So just click on sort by pressure.
Okay.
And click it
that's
twice
fine.
so that you have the high pressure, that's reservoir, bottom hole, and etc.
Yes, correct. Now I can calculate. Thank you.
No problem. Yeah, that happens. So go to the plot. Oops, see, I changed something. Maybe the locations, and then I need to plot. I need to plot again. Okay, so the plot that I was previously showing is the scaling scenario. And what is plotting here, you'll see that in the y-axis, we are plotting what we call the dominant pre-scaling tendencies versus the locations, okay? What do we mean by dominant pre-scaling tendencies? So this is a funny name, but really what we are saying there is that we are plotting 5 minerals, the 5 minerals that have the highest pre-scaling values compared to all of the other possible minerals that can form. The software goes and select the highest pre-scaling values, and those are the ones that are shown in this plot. Okay, so as we defined earlier, pre-scaling values are essentially saturation ratios. Or we can also see the saturation ratios are as the driving force for precipitation. And that's what we are plotting here. Again, the x-axis is the different locations of production. We can see in this plot that barite, which is the red core, this red value here at the beginning, at reservoir conditions, you see that the value is equal to 1. And this is what we told the software is because we are saying that the reservoir is saturated with barite and calcite. So we assume that the fluid was in equilibrium with the reservoir matrix. But as we are producing this fluid, the scaling risk of barite increases. And now the values are significantly higher than 1. The reason, what is the reason why we see this increase in the barite scaling tendencies at each location? And the reason is because the temperature is decreasing, right? And the barite saturation is temperature sensitive, and that's what we are seeing here. On the other hand, we have...
Sorry.
Yes.
Sorry. Is there a way to add on this graph other process parameters?
Yes.
To see basically the inter-reactions with pressure and temperature.
Okay, so you would like to see...
I mean, yes, multiple scale,
yes.
multiple graph, yes.
Oh yeah, yes, I will show you that in 1 second, okay?
Okay.
Good question. Okay, so you'll see that calcite here is also saturated at the beginning, and you increase the locations. You change the locations, you decrease your temperature and pressure, and you'll see that it becomes undersaturated at the separated location. Okay, so as the question just raised up, this is only the pre-scaling tendencies, and maybe we just don't want to see the pre-scaling tendencies only. We are interested to see, let's say, the amount of solids, or you also want to plot the temperature or pressures. But yeah, so you don't want to see this. So there is an option in the software where you can select the variables that you want to plot. So you'll see in the upper right corner, you'll see 3 buttons. You have the view data, you have the variables, and you have options. Let's click on variables. That will open a new window. You will see to the left, under the tab that says curves, you can see all the possible variables that you can plot in this plot that we have here. So the current plot that we have is saying that we are plotting in the x-axis, the locations, and in the y1 axis, we have the dominant pre-scaling tendencies. Okay, but you could also add in another, in the y2 axis to the right, you can also add some other categories if you want. So let's say I want to add a solid category. I want to see how much of that solid that the software is predicting to form, or those minerals that are predicting to form. I want how much they are actually forming, the value of the solids, the solid amount. So I'm going to go to solid, the solid category, and you'll see that there is barite and calcite. Select barite, and I want to put it in the y2 axis. So what I'm going to do is I'm going to use this right arrow here to put it in the y2 axis. And I will do the same for calcite. And now I have added those 2. You can click apply to see that now the software has added a y2 axis, and it has added the solids, the amount of solids that are being formed, and the units are in milligrams per liter. Now for the y1 axis, I don't want to plot that many solids. I had 5 different solids. So I'm going to double click to remove that. And I'm going to go back to the prescaling tendencies or saturation ratios. And since I know that calcite and barite were formed, I'll select the barite and put in the y1 axis, and then the calcite and put in the y1 axis. Perfect. Now, there was a question about, okay, I want to know pressure and temperature. That will be found under the stream parameters. So let's say you want to add the temperature, and I don't know what to, let's put it in the y2 axis, and then click apply. And then click, maybe you also want to see the pressure. Well, the pressure will be very high, I will just make the plot different, but okay, let's just stick with temperature. Okay, so in here, you will be seeing 5 different lines, one that represents the solid prescaling tendency, the one that I just talked about. Then we have the amount of solids of calcite and barite and how much is forming. For example, this blue line here is saying that calcite is the highest at the wellhead with a concentration of 21 milligrams per liter, right? And then the temperature will be given by this curve in here. You see here. So you see how the temperature starts at 125 degrees C, and then it decreases to a separator value that is 60 degrees C. Okay, so I am going to remove this temperature because I want to show you another way of saving a plot for future usage. I'm going to right click on this temperature curve. And I hope that I answered your question about how to add more components.
Yes, you did, Diana. Thank you.
Oh, great. So I'm going to right click on it, and I'm going to click the option remove. And this is the plot that I wanted to see. I wanted to see the prescaling tendencies combined with the solid amount. Okay. So I want to talk about a third panel that we have to the left. That's the plot template manager. Maybe you always want to analyze slightly change. Maybe you want to analyze the same reservoir 3, 4, 5 different times, and maybe there is a slightly different changes in the brine analysis or in the gas analysis. So you don't always want to go here and go to variables and select the variables you want to plot in the y1 axis and the y2 axis. That's too much. It's a lot of time. It's time consuming. So there is an option to save this default plot that will tell you the prescaling and the solid amount. That is in the plot template manager. At the moment, you see that I have created different plots here, but I want to save this plot as prescaling and amount of solids plot. So you see that down here there is a white section, like a box that is a white section. And in there, I have the capability to type the name of this plot. This plot will be pre-scale and amount of solid. That's a long name, but that's where I want to save it. So then you'll see the option here, save. Click on it. And immediately you'll see that the pre-scale and amount of solid plot goes to the plot template manager. So if you want to see the default plot, you can click on the default plot. This was the original plot. But you want to go back to the pre-scale and amount of solid, you just click on that pre-scale and amount of solid, and then you go back to the actual variables that you want to see. I hope that was clear. I find it very useful, especially when you do a lot of calculations and you don't want to plot over and over and over again, so it becomes very handy, very, very handy. And that is regarding the template manager. Okay, let me see what else I wanted to talk about in here. So far we have spent this much time building the case. But you will see that as we continue this class, all of these steps will be repeated and if you feel more confident on how to set up a self-scale, well, now with these steps, now you will be very confident to set up your own scaling analysis for your specific well. So those are the these are 4 different objects that I want to talk about. There is a last one that I want to add today, or the one that I want to talk about today. And that is the contour diagram. This contour diagram is very useful when you want to see how different fluid properties change as a function of temperature and pressure. Okay, so you will be able to see which scales will form a specific temperature and pressure, and maybe you can also see some other variables like how the pH changes at different temperatures and pressures, etc. So we will use these last minutes of today to set up this case, and then we can go ahead next time to create the second example that will contain the oil phase example. Okay, we just go back to the software, and then we are going to go to the actions pane here, where you'll need to select the add scale contour. Double click on it, and then we can name this as Olympus contour. Oops. Great. So we are going to do something similar like we did in the Olympus production. We are going to bring the contents of the Olympus reservoir to this Olympus contour diagram. So what I'm going to do, actually there is an option that is really cool, and you can just select or just go to the Olympus reservoir, click on it, and then drag the contents to the inlets tab of the contour. Okay, so what I did is I click on it, hold the click, and then move it and drag it towards the inlets tab of this Olympus contour. If for some reason, oh, I created something here. If for some reason it just doesn't work, we can always just go to the type of fluid, select whole fluid. We select the Olympus reservoir, and again, we will leave the automatic flow rate. Okay. Next step is to go to the conditions tab, and in here what we are going to do is to define the temperature and pressure range that we want to study, right? So we wanted to say that for this case, we wanted to study the lowest temperature. We want to start with the lowest temperature and with the highest temperature during production. And we want to plot several points in between. So if you remember, if we go back to the Olympus production, in our conditions, we saw that our lowest temperature was 60 and our higher temperature was 125. The lowest pressure was 30 and the highest was 275. So I will use these values to define the Olympus contour. So for the temperature range, we will start with 60. The high value is going to be 125. And we're going to do, this is a good one. Well, let me see. I'm going to make it very refined. Since we have the time, you can leave it running. Okay, so what I'm going to do is increments of 2. Okay. And then, no, this is number of steps. No, I want increments of 2. Make sure, okay, there's total of 33 number of steps with an increment of 2 degrees C. Now we go to the pressure. For pressure, please uncheck this log scale here. I don't want it there. I want to just use a linear scale. So I'm just uncheck it. And the lowest value for pressure will be 30 bar. And for the end value, I want 275. That's the highest value that we had. Great. For the increments, I'm going to use 5. Okay, 5. Great. So now we have removed this log scale. We have defined our, this is our range of operations for temperature and pressure. And the next step now is to go to the solid step. This is familiar to us. Then we will just select the standard option. And I don't know what to do here. Maybe at the end of the class, we can click on calculate, because this will take approximately, I'll say like 15 minutes, 20 minutes, and by that time the class will be over. But once the class is done, we will go back here and click on the calculate button, and next time we will analyze the results of this object. But at the moment we have defined it, so let's not click on the calculate button at the moment. Okay. Okay, so now this is a summary of what we have done so far for the Olympus.
Diana,
yes.
Are you using the Olympus contour as a sensitivity analysis to basically evaluate the amount of solid that you have in a particular process or perimeter conditions? Is that the case here?
Yes, that is the case. So you'll see this is just a screenshot of one of the results that we will be analyzing. And in here, I am saying the total solid concentration in milligrams per liter. And I am doing a survey, a sensitivity analysis. I'm saying at this pressure and at this temperature, will I have a total solid concentration?
Okay.
The maximum amount will be in these conditions, the lowest amount will be in these conditions, etc. And because this calculation, you'll see that it's very refined. It has several points. It will take like maybe 15 to 20 minutes. And I just wanted to let it set up so that before we end the class, we just let it run, and tomorrow we can analyze that.
Okay, but just a quick one. If I know this contour diagram might take time, by adding to my original trend the stream pressure and temperature on the plot, which we saved. If you go to plot template manager, and then you add the variables as temperature and pressure, can't you also read there, because the condition haven't changed in terms of temperature and pressure as the input condition? So can't you just use it? Yeah, this tab. If I had the pressure and temperature, I'm still able to read basically in which location what is the impact my pressure does on my amount of solid in a certain location around my system, and on which conditions. If I know the contour, is it still the same result with the Olympus contour, or the Olympus contour give you the another one?
No, okay. You're right. It will be the same results. Not a problem. This is not a problem. The thing is with the this scaling scenario, you can add maybe 1, 2, 3, 4, 20 different locations, okay? With the Olympus contour, you can add a wider range of points. So let's say you wanted to analyze a whole range, like maybe you wanted to see the sensitivity as maybe the temperature changes every 5 degrees C, every 10 degrees C, you know? So you just have like a bigger picture of what happened, what pressure and temperature are doing.
Understood.
But the results that you see in here, in this Olympus production of this combination of temperature and pressure, will be the same. And in the contour diagram will be exactly the same.
Understood. The contour is just more refined from what I've seen. Okay.
More refined, and it just gives you a bigger picture with colors, and then you have an understanding of where you may be located. And here is like, okay, this is what happens at each location. The other one is what happens in a matrix of combinations. That's the difference. Nothing else different about it. So, but again, the question was also as well before, like you can always add the temperature and pressure in this scaling scenario, and you'll see what happens in this temperature and this pressure and what is the scaling tendency, right? You can always do that. Let me just save that. Okay. Okay. So we will, at the end of the class, we will click on calculate just to continue with this. Okay, so to wrap up, so far, what we have done. So we have created our representative brine. We did a balance. We did a charge balance. We reconciled it for, we did a charge balance. That was our reconciliation. Then we created a gas and we also reconciled it. And we found out that it was slightly saturated with water. Then what we did is we brought that brine and that gas to a saturator. We entered the streams and the flows. We entered the mineral data. We said we want to saturate it with calcite and barite because those were the cementing materials of the reservoir. And then we will review if there were chemical changes or not. After we were happy with our reservoir fluid, then we took it to a scaling scenario, or in this case, the last example was a contour diagram. We entered the process conditions, and then we analyzed the mineral scales that we may have obtained for that specific production. So that's what we did. And that's what we will be doing in our next example. This next example will be very similar, but well, it's slightly different regarding the analysis. It's going to be a little bit more complex. We are going to do saturation in a slightly different way. We will be doing this next class. And then we will be working on our third example that I was asked today, which is the bath as well, where we will learn how to enter an oil analysis. And we will do the same. We will have a water analysis, gas analysis, and an oil analysis. We'll bring it to saturation and understand the results. So let's go back to software and let's click calculate on that specific object, calculate. And you can go to the plot, and in there you will see how that matrix of temperature and pressure will start being plotted. And with this, I think that I just don't want to cover or go through another example because this is the top of the hour, but I can take any questions at the moment before we go, and anything that Mike also want to add.
Diana, I have a quick question for you. Could you please share the value you use for the Olympus gas stream again? Sorry, I missed those.
For the gas, you mean for the reservoir? Yeah. Okay.
Yeah, I couldn't find it in the manual.
Yes, so it's 250,000 standard cubic meters.
Okay, thank you.
Yes, no problem. We will be sending. I will be sending this file for you today.
Oh, great! Thank you so much.
So you can compare it, and also we will be sending the recording session. Any other question?
Yeah, I have one question regarding the scale contour condition. The comparison we made after the result, for example, yeah, it is that one. It will concern the reservoir or the point we want to focus on. I mean, maybe at the surface or at the reservoir. Or it is about the whole system.
This is
scale contour.
This is the scale contour diagram. I don't know if I am showing it.
So that means it doesn't depend on the condition. I mean, if you are in the reservoir or at the surface.
Yes, well, what happens is, let's say, we already know that at reservoir conditions, we have 125 degrees C and 275 bar, right? So that means if you go to the Olympus contour, you find for that combination, you find for 125 and 275 bar. 175. and 200 will be this point up here. This will be reservoir, right? And you will just analyze the results here. But if you just want to see this, just want to see the specific point, you can just go to the scaling scenario here, where it will just tell you specifically at that point. The thing is that probably you want to also know what happens if you decrease the pressure just a little bit. So you will be, and maybe you are in the same temperature. So you will see that information here in this contour plot. Or,
yeah, for example, at the manifold, yeah, okay, I see.
Yeah, so this will be at the reservoir, right? And down here, if you go like kind of diagonal to the other extreme, this will be separator conditions. So what this will give you is a visual representation of what you will be having at separator and what you will be having at reservoir, and anything in the middle. Okay.
Okay.
Yeah, it's I personally like it. It's just a way of seeing the results more visually, and it just gives you an idea of, let's say you want to understand what happens if you increase the temperature or you change. You want to see how the CO2 solubility changes, for example, or you want to see how the calcite scale changes as a function of temperature and pressure. And we will see that first thing in next class, in the next session. But we will need to wait for this to be done, and then we can talk about it. But yes, with this, I will just let you go. And please let me know if you have any questions. You can reach me or Mike or send us an email if you have any questions. We'll be here to help you with this. And also, if you have any cases that you're interested that we cover next class, let me know. You can send a case and we can go through it during the class next time.
Yes,
Okay.
an interesting one, yeah, Dinah. I know earlier on when Mike started the introduction, he said that we might not cover the corrosion prediction calculations.
Right.
Something that I was looking forward to in this course. I'm working on a particular case. In that regard, it's also interesting because you mentioned the fact that we can basically bring the tools, the add-on into pipe sim, because I'm working on the pipe sim on a particular pipeline export. And basically I'm trying to determine the optimum temperature based on the optimum flow with the available pipe wall thickness, which is basically due to a reduced pipe wall thickness due to the corrosion rate, which has already been lowering, if you want, the capacity, the maximum flow capacity of the system. So that was really an interesting tools to basically see how I can import first of all, calculate the corrosion rate based on the pipe wall thickness and the different case flow and temperature that I have, and import it to see if it's quite predicting with the last inspection result regarding my corrosion rate allowance and then the design year life of my pipeline. So I don't know how we can probably take it offline or have a talk or a chat, or if I will have the opportunity to go through one example that you may have to predict the corrosion rate on a particular case.
Yes, we can do that next class. We can maybe use the reservoir, the Olympus reservoir as an example. Let me just write it down before I forget. and I can show you how you can do basic corrosion rate calculation, and also you can do it. You see how we are doing this contour?
Yes.
You can do the same thing for the corrosion rate.
Okay, I think the best case maybe would be to take it from the facilities. As you mentioned, I think in one of the module that will be covering, if I'm not mistaken.
Yes, we'll do facilities.
There will be the facilities, exactly. On that facilities, I see there will be pipeline, basically calculation, I mean, scaling calculation on the pipeline, if we can take it from there, from basically the facilities, how we do the corrosion calculation, that would be very useful.
Okay, yes, definitely, I'll do that. Any material in particular?
No, not really, not really. Any case should be working for it. We basically mostly in the oil and gas multi-phase fluid. Of course, I'm talking about an export pipeline, so it will be assuming no gas and trend gas or mostly gross, basically oil and water. But any case should be fine as long as I understand how it runs. Then I should be able to apply it to anything further.
Yes.
Thanks, Diana, for the presentation. It was really great. Thanks.
No
for your
problem.
assistance.
Thank you all for your time. I don't know, Mike, if you want to add something. If not, we can next week.
I want to add a couple of things. One specific to the folks from Asala. I had talked to Serge about setting up a separate class with Diana to cover corrosion analyzer, because I know that's part of your license, and it was something that he asked about specifically. So we can absolutely look for another session under your service contract to set that up, but we can deal with that separately. For the rest of the group, if anyone is still on, Eric, I saw your message in the chat about the training manual. I'll get with Dira and make sure we get you a copy of that for sure. Otherwise, you guys have a couple of days away from us, so try and use the software. Diana already mentioned you'll get the recording in her cases, so if you want to work through some other cases of your own, if you want to retry what we've done in this class, just kind of play around with it, get used to the software, see then what questions you have. And what we'll do is we'll start Wednesday's session with any questions that you have on today's material. If there aren't any, no problem, we'll go straight into new stuff. But if anybody does run into things that you want to cover before we get into new material on Wednesday, that would be great. So thanks everybody for the time. I know it's hard to get a 3-hour block when you've got a full-time job that you're working on too. So we appreciate you taking the time to join us, and we will see you again on Wednesday.
Thank you so much. Bye-bye.
Thank you, Mike. Cheers. Bye.
Thank you, Mike. Thank you.